Welcome back, everybody. We are going to start our probability unit with an introduction just of some basic probability vocabulary. So probability is the mathematical study of uncertain or chance events. It's usually written in fraction form with the number of desired outcomes over the number of possible outcomes. An outcome is any possible result. So for example, if we were playing rock, paper, scissors, rock, paper, and scissors are possible results of the game. And so those would be called possible outcomes. A simple event is one outcome or a collection of outcomes, usually just from one thing, like rock, paper, scissors, or flipping a coin, or spinning a spinner, or pulling a card from a deck. We're just doing one thing. When is something random? It is random when it occurs by chance. So there's not any way for you to be able to pull strings or force something to go the way that you want it to. And last but not least, for this part, complementary events is when the sum of the probability is 100% or one whole. So let's take a look at some examples. I have a number spinner. There are 4 possible outcomes because I have 4 possible values that the spinner can land on. And so our first probability, the probability that a number is prime. Remember, a prime number can only be divided by 1 or itself. And so 1, 2, and 3 are all prime numbers. That's 3 desired. 3 of them are prime out of 4 possible outcomes. The probability that it's not prime then, remember, can be divided by more than 1 in itself, and that's 4. It can be divided by 1, 2, or 4, and there's only one of those. So 1 desired outcome out of 4 possible outcomes. If I added these probabilities together, 3/4 plus 1/4 is 1 whole. And that means that these are complementary events, having a prime number and a not prime number. The dates of the days in the month of February are placed in a hat, drawn in random, and then replaced. That's going to become important as we start talking about different types of probabilities. But being replaced means I'm going to draw the 5th of February and I'll put it back into the hat. So what is the probability that the number we drew is even? Remember, there are 28 days in February, and half of those would have to be even. So 14 out of 28, which is 1/2. Remember, we always want our fractions to be in simplest form. So 14 out of 28 gets us started, but 1/2 is the answer that we're going to give. the probability that the number only has one digit. So that would be the first, second, third, fourth, fifth, sixth, seventh, 8th, and 9th of February. That's 9 numbers. So 9 days out of 28 days. And we can't reduce that. 9 and 28 don't have any common factors that we can simplify from. Numbers ending in 4. So we have the 4th, the 14th, and the 24th. That's 3 numbers. So we have 3 desired out of 28 total outcomes, because again, 28 days. So we have 3 28s. Can't simplify that, so that's done. Some more vocabulary for us. A sample space. A sample space is the set of all possible outcomes. So all the different ways that something can be answered or spun or flipped or rolled or anything like that. A tree diagram helps to display outcomes. So we're going to work on a tree diagram so you can see what it looks like. The Smiths want to know the probability of having 3 boys in different years. So your choice for the first baby is a boy or a girl. After the first baby, you have a choice of a boy or a girl, regardless of if you had a boy or a girl to start with. The third baby, you still have a choice of boy or girl. And that would be regardless of what you had for your second baby. And so we make a list of outcomes over here. And we follow along our tree diagram. We have boy, boy, boy. And then boy, boy, girl. Now we're done with this. So we come here. Boy, girl, boy. We're following the branches of the tree diagram. Boy, girl, girl. So we finish with that top one. Now we're going to work on the girl part. Okay. So we have girl, boy, boy. Girl, boy, girl. Girl, girl, boy. And then the last set of branches, we have girl, girl, girl. So this is our set list of possible outcomes, which is also our sample space. Our sample space and our list of possible outcomes are the same thing. So how many outcomes do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8. 8 possible outcomes. So the possibility of having 3 boys. Well, there's only one here in our list where all of them are boys, and that's the very first one that we did. So there's one possibility out of 8 total possible outcomes. The possibility of it being all girls. Well, there's only one possibility of all girls, and that's here at the very bottom. So that is, again, 1 out of 8 possible. The possibility of having 2 boys and 1 girl. Now, it doesn't say what order. So it just says we have to have 2 boys and 1 girl. So 2 boys, 2 boys, 2 boys. And that's it. So I have 1, 2, 3. 3 out of the 8. Then it says that we have 2 girls and 1 boy. So 2 girls, and 2 girls. So that's again 3. So 3 out of 8. It's asking us for the total. So I'm going to do that above this screencastify bar here. We have 1/8 for the all boys, 1/8 for the all girls, 3/8 for 2 boys and 1 girl, and 3/8 for 2 girls and 1 boy. These already all have a common denominator, so 1 plus 1 plus 3 plus 3 is 8, which gives us a 1. That means in this blank that's hiding right here, these are complementary events because they total 1 or 100%. Judy tosses a coin 4 times. Draw a tree diagram showing the possible outcomes. So I have my first toss, my second toss, my third toss, and my fourth toss. And then we have our outcomes. So we have on our first coin toss, you have a possibility of heads or tails. Then I flip the coin again. I still have a possibility of heads or tails regardless of whichever one landed first because I haven't changed the coin. Then on our third toss, regardless of what landed on our second one, our coin is still the same, still has a heads and a tails. So we still have heads or tails being possible regardless of what the outcome was of our second toss. And then our fourth one, we still have, again, heads or tails because we're not changing the coin. The coin always has heads or tails. And so regardless of our outcome in the third toss, I always have heads or tails as a possible outcome for the fourth one. So my tree's looking a little sickly here, but that's okay. So listing the outcomes. Now we got to follow our branches. I'm going to start over here with purple and heads. So we have heads, 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 heads. That took care of that one. Heads, 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 tails. So we've used that branch. Heads, heads, tails, heads. And then heads, heads, tails, tails. So these are done. And we're moving on to the next part. Oops. So I use this one. All right, we have heads, tails, heads, heads. Heads, tails, heads, tails. This is done. Heads, tails, tails, heads. Heads, tails, tails, tails. All right, we've used up that whole top half of our tree. Tails. So tails, heads, heads, heads. Tails, heads, heads, tails. Oops, I think I messed up here. That was... Oops, I wrote it again. I need a heads there. There we go. So that takes care of this. Tails, heads, tails, heads. And then tails, heads, tails, tails. Tails, tails, heads, heads. tails, tails, heads, tails, 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 heads, and tails, 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 tails. All right, so there are all of our possible outcomes. If we count them up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 possible outcomes. So what is the probability of getting at least 2 tails? Well, let's see. Only one tail. Oh, here's one set. 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like 10. Let's double check. 2 tails. It says at least. So that means it could be 2 tails, 3 tails, or 4 tails. So here's 1, 2, 3. Oops, there I missed one. 4, 5, 6, 7, 8, 9, 10, 11. So that is 11 out of 16 total possible outcomes. It asks now, what is the probability of getting first 2 heads, then 2 tails? So that is asking you for a specific order. And this one right here, our fourth one, is the only one that works. So it's 1 out of 16. All right, our last vocabulary word for today is the counting principle. And the counting principle is used to find the number of possible outcomes. And we find this by multiplying the individual possibilities. So if I go back to that coin problem we just did our tree diagram for, we had 4 tosses, and our choices for each toss were heads or tails, heads or tails, heads or tails, heads or tails. 2 for each one. So if we multiply these together, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. And when we counted our list of outcomes, there were 16 there. So much easier to look at it that way rather than having to count everything out. It's also a good way to make sure that you have all of your possible outcomes listed. So let's take a look at these dishes. There's 3 possible main dishes. There's 2 sides, and there's 2 drinks. So 3 times 2 times 2 gives us 12 outcomes. So if we were to make a tree diagram or start listing all the possible combinations, we should end up with a total of 12. Shoes. We have 6 styles in 3 colors and 9 sizes. 6 styles in 3 colors and 9 sizes. So 6 times 3 is 18. 18 times 9 is 162. So there'd be 162 possible outcomes. The jeweler can sell you a diamond in one of 7 sizes and 7 cut styles. So we have 7 sizes, 7 cut styles. 7 times 7 is 49 possible combinations for the diamond, or 49 outcomes. Cars, we have 5 models in 3 colors and 3 different engines. 5 times 3 times 3 gives us 45 possible outcomes or combinations of car model, color, and engine type. That's going to conclude our very first lesson in reviewing basic probability. Have a great night.